Welcome to O10 Trix, Only Library Implementers Know. My name is Jonathan Wakely.
And he's Marshall Clow.
And unfortunately, due to a subtle mix-up, neither of us has a red hat in hand or on our heads. But anyway, so we're going to talk about, we'll start with what we do. We work on standard library implementations, different library implementations. We compete friendlily, and occasionally we gang up on other library implementers. And
Make sure we're right, and
they can be right or wrong.
They can do what they want, but we're right. Yeah.
Exactly.
It was decided recently, in joking, that because our implementations have names, the Microsoft one doesn't. People just refer to it as VC++ standard library, or MS STL. But given that one of their main guys is called STL, people suggested it should be STL STL. Which, but if they can have a sort of a duplicated name, then we can be whatever that is.
That's just a lot of letters and a lot of pluses. Anyway, what do we mean about Trix?
It's just clickbait title to get everyone in, isn't it?
Pretty much, but I mean, there is something to be said for Trix. They're techniques that we use in our standard library implementations that might be more generally useful outside of standard library implementations, but we don't see people being aware of them or using them.
Some of them are quite simple. Some may be unsurprising. Some might be more than you'd ever need to use in a library that you're writing yourself. But when you're writing the standard library, you've really got to shave off. You can't have any overhead. You've got to trim off all the excess fat. Or some user somewhere will complain that your implementation is not as fast as one they wrote themselves could be.
I see some of those people here in the room.
No, they wouldn't.
All right, so we'll start off with the first one. Empty base class optimizations. Okay, so when you're writing generic code, sometimes you delegate some of the design choices to a user-provided class, a traits class or an auxiliary class or something like that. In unique pointer, for example, and shared pointer, they have a deleter that controls how the resource gets disposed, and default deleter is the default one that the standard library provides, and that's what you get if you don't specify your own. Set and map and a bunch of algorithms have a comparison operator that controls how things get sorted or how your set gets ordered. All the containers, well, except array, have an allocator. Sometimes these objects are very small. They don't really carry a lot of data with them, and in fact, sometimes they're empty. They have no data members at all.
Yeah, they just provide behavior, but not state or identity.
And interestingly enough, the standard library provides a type trait that's called isEmpty, that you could give it a type, and it will tell you if it has no state. Reading the definition of isEmpty in the standard is actually quite amusing because it goes into some details that you might not have thought of. It has phrases like, shall have no non-static data members except for bit fields of length 0. And from that then you end up on a voyage of discovery, discover that bit fields are not really member variables, and it's just.
And they don't have a type, or not a type in the type system. Yeah.
They're just, you discover that there are weird corners of language that you never even thought about. And you don't want to.
But it's our job to.
Anyway, if these objects have no state, there's no reason to store them, right? Actually storing them doesn't provide you with anything. It makes your objects bigger, okay? So you can just magic one up, construct one when you need it, use it, throw it away. Because if it has no state, all copies of the object are the same. But basically, all the standard library implementations that I've looked at have a facility for not storing empty objects in their in a bunch of the classes. This is, again, as Jonathan said, this is, we want to pare all the fat out. And basically, you want to just, well, as I said, not store them. In C++ 2a, and then upcoming C++ 20 or whatever it's going to be called, we recently adopted into the standard an attribute called no unique address, which will enshrine this kind of facility in the language. Basically, the reason you have to play games with this is because the language rules that we inherited from C and we've used for many, many years, it basically says every member has a unique address, has to have a unique address, and the smallest addressable unit is a byte. So the minimum size for a member variable, excluding bit fields, is a byte.
And
so
when you have a base class, the language says that's not necessarily true. Base classes don't have to take up space, even if the size of the object is non-zero. When it's a base class, you can have multiple objects that all exist at the same location, at the same address. But it didn't allow that for member variables. So yeah, you end up with these tricks of things like compressed pair, or in our library, we don't have a reusable utility. We just create a new type every time we need it that derives from this stateless, possibly empty thing, so that if it's empty, you get the empty base class optimization. If it's not, you don't get that, but it needs size if it's not empty anyway, so it's no loss.
And then in C++ 17, the rest of the committee came along and stabbed Jonathan in the back by introducing the keyword final.
Because you can't derive from it if it's final, so please don't put final on your allocators, because you won't be able to use them with my library, because I just assume I can inherit from it. And
another color band final.
Yeah. No, there are actual really good reasons to have final. They're just really rare. What?
Just not for allocators.
Not for allocators, no.
Or comparison functions, or just don't put final on stuff you're going to give to my library. It works for tuple, because I specifically detect if it's empty and not final, then we try and inherit from it. But there are ways to make things final without the final keyword, like having a protected destructor or other things that prevent you from deriving from it. We can't detect them, so just don't do things in C++, it won't work. Just no things.
No things. Anyway, so I already touched on this before, but why is it important? If you store them, they take up space in the object, and there's no good reason to take up this space. In unique pointer, right, unique pointer has two fields. It has a pointer and it has a deleter. Okay, the pointer is, let's say, 4 bytes. Okay, if we store the deleter and it's empty, it's still going to take up a byte. That means that the unique pointer is going to be 8 bytes long due to alignment restrictions. That's twice as big. And if you have a vector of them, you have 1,000 of them, suddenly your vector is holding 8,000 bytes, of which 4,000 bytes are just nothing, empty space. Padding. Thank you, that's the word I was looking for. And there's no point in that. So we don't store the deleter when we don't have to. And that's true for, as you saw the list a few slides back. Allocators, if they're empty. Comparison functions. By the way, hash functions. By the way, if you have a comparison function and you pass in a function pointer, a pointer to a C-style function, okay, we have to store that. We have to store that function pointer. That's 4 bytes, 8 bytes, whatever it is. Okay? But if you have a class with a function call operator and no member variables, we don't have to store that. So there's something you can do to reduce the memory overhead of your data structures if you use auto pointer. Yeah, right. Unique pointer, map, set, all of those. So you want to prefer to write simple classes, function objects rather than passing around function pointers.
Or lambdas, which a lambda that calls the function f will take up less space than the function pointer to f.
Yeah.
Because a lambda, well, it should be an empty class,
Should
even
be.
if it's doing the same thing as that function. Peter?
You're not allowed to take the address of the standard library function, even though Marshall doesn't believe me yet. But Jonathan will know.
Jonathan and I have not had that conversation yet. Yes, very much a better time than now. All right. Any questions about this one?
Please do interrupt at any point, by the way. Then just jump, yeah.
Can lambda captures benefit from idiom?
No, if you have captures, they're required to be data members.
Can we change that?
It's probably not observable. The standard says they are members, but yeah, possibly because you can't do anything that could tell the difference other than size of, but the size is unspecified anyway. Yeah, it's possible that the compiler could choose to use that, but with no unique address, it could do other ways of taking up no space anyway. It would be an odd choice to capture something with no state anyway, yeah.
Yes, yes, it would. Well, on the other hand, you might, in generic code, you might just capture something and discover at instantiation time that it was empty.
Yeah. You didn't know until it was too late.
Okay. Next one, constraining greedy templates.
So some types can be constructed from nearly anything. Sometimes that's bad. We have a couple of defects saying the file system path can be constructed from anything under the sun. We didn't mean it to be. Some things you specifically want them to be constructed from anything, and it's what it says in the name. C++ 17 added the any type, and you can store almost anything in it. So obviously it has a constructor that takes anything, and it will stash that inside itself, do type erasure. It should be nearly anything. What you don't want is for trying to copy the object. Any is copyable, but what you don't want is for A2 here to say, I can store one of them. I can store anything. I'll do that for you. And the reason this happens is that A1 is non-const here. We have a non-const L value. The copy constructor that gets defined for this type, whether you do it manually or the compiler does it, is a const L value reference, and the conversion from non-const to const is a conversion, and this constructor would bind without any, or just with reference binding, which is a preferable conversion sequence. So this would choose to use that constructor instead of the copy constructor, even though you're clearly saying, I've got two things of the same type, I want to copy one into the other.
And then you would end up with an any.
You get any's of any's.
Any holding an any.
Probably didn't mean that to happen, because you're going to have to use a lot of any casts every time you try and get anything out.
All right.
So the obvious solution, this is a lot of the things we're going to look at in the next few items involve simply putting a spin constraint on it. So here's our first one. We're gonna see what we can put on this. One trick we don't have, unfortunately, is getting any of this stuff to be readable or fit on slides easily. This is a recurring problem in standard libraries, because the examples we're showing here are simplified, and they still struggle to wrap and fit on the slide in any kind of readable way. So please don't take any of this indentation as how you should indent things. But the solution here is to say, right, we only want to use this constructor template when T is not the type that we're constructing. Please don't use this instead of a copy constructor. So the way you do that, decay T, the decay type trait will strip off references, CV qualifiers. It will also turn arrays and functions into pointers. We don't actually care about that bit here, but the important thing is to say, if this gets deduced as an L value reference, lose that reference. If it gets deduced as const int or const anything, throw that away and then see if it is any. and we only enable this constructor if it's not the same as any. So do not try and use this instead of a copy constructor. I actually end up having to do this in lots and lots of places. Std function needs it because that can take anything callable thing, but then you want to constrain that constructor to only be callable things. You don't want to allow an int to be put inside your std function. And these finite constraints for function, that after this there'd be other things saying, is it callable? Certainly with my compiler, those constraints blow up if function ends up getting inside those constraints. So you're trying to say, is this callable? And it's, oh, it's a function, yes. This is callable with that signature. But it's still an incomplete type at that point because you're in the constructor and it crashes in flames. So I need to, before I try and see if it's callable, I need to rule out myself, like, if it's not a function, do some other things. And I end up needing that in surprising number of places. The first thing you do is go like, right, assuming I'm not this type, do other stuff. Right. It becomes surprisingly common when you're trying to handle, as we say, the standard library has to cope with everything that's thrown at it.
Yes, you people are frequently not our friends.
Yeah, so as I said, decay has some, it also decays, as in the name, the arrays get decayed to pointers and functions get decayed to function pointers. We don't actually care about that here because if it was an array or a function, it's not any anyway. So in this case, we could have used remove CVRef just to sort of throw away the references and the CV qualifiers. That's coming in the next version of C++. And it's a sort of slightly weaker form of decay when you don't actually need the full decay semantics. But decay, in almost all cases, decay does the right thing for you, even if actually it would do a bit more in other cases as well.
Yeah, that's the thing is remove CVRef is basically is a strict subset of decay. It's just sometimes you don't need all of decay. Okay.
Oh, we were going to say, yeah, so we've both got things like remove CVRef in our libraries already, even though it's not coming until C++ 20. A lot of the time, because our implementations have to still compile in C++ 11 mode or C++ 14 mode, a lot of the time we add these new traits, put a double underscore version of it, so we can use it internally before it's supposed to be declared, and then in the C++ 20 mode or whatever, the public version to it is just a using declaration or an alias template for the one we've had all along and we're using internally.
Yeah, the flip side of that is if you're a masochist or you have the random habit of reading standard library sources, but I repeat myself, you will notice that a lot of things in the standard library do not use the latest C++ features, like say const per if or something like that, even though it would simplify the code greatly. And the reason for that is because we have users who compile the standard, who compile programs using the standard library with C++ 98 or 11 or 14, and it would just blow up, their programs would blow up, fail to compile.
So yeah, even if our implementation has the new features in it, we can't use it inside that implementation. That can be frustrating. I know this feature's here, I just added it.
Exactly. Or my friendly compiler guy just added this. Great, no, I can't use it. All right, next up.
Right, so we start to get into something a bit meatier than the bit of template metaprogramming. So if you've got something that wants to apply a meta function, so meta function is a template class that has a nested type, that this is the result of this meta function. So this meta function says, given a t, it will transform that into t second type. But the stood pair would be a suitable argument for this. So for example, we use something very like this inside our red-black tree implementation so that the same code can be shared by map and set. When you want to get, it would be for first, not for second, but when you want to get the key from the value type stored, we have the same generic code for the red-black tree, and then we use a meta function like this to say, either get me the first member of the pair, which is the key for a map, or just get me the thing itself, because for a set, the thing itself is the key. So yeah, if you've got something like transform t that applies a meta function, if you pop onto the next slide, there are times like with std set where your transformation that you want is actually the identity function. You don't want to do anything. Like for std set, you just want to say the whole value type is the key. So it's quite common, and I mean, we've still got one because, again, we can't use the new thing that we're about to demonstrate. Right. But a lot of standard libraries will have something like an __ identity or __ self or something that just doesn't do anything. It doesn't transform anything, but it's a transformation trait, technically. There's actually a nicer way to do this now. And the other place that is more useful in outside standard libraries, probably, you can use an identity function to create a non-deduced context. If you've got this function that takes some t, and it wants to do something for every element in this vector, unfortunately, it fails if you mix the types. So if you've got a vector of longs, and you're like, oh, yeah, I just want to multiply everything in it by 5. 5 is an int. And the compiler will say to you, wait a minute, I can't multiply a vector of longs by an int. That's crazy talk. And the problem is that it uses t in 2 places here. And they will both participate in deduction. And here it will say, yeah, t's a long. Yep, got it. OK, wait, t's an int. And it doesn't have there's no rule for saying, for runoff and deciding which of these should win. And this happens surprisingly often. We just fixed standard atomic in a lot of ways to avoid this sort of thing, because if you tried to add 5 to an atomic long, you get exactly this problem. So you're like, oh, OK, 5L, fine. You shouldn't really have to, it shouldn't be that hard for the compiler to add 5 to an atomic long.
Right, and then you end up with, that just pushes the problem off on you, because if you're trying to write generic code caking atomics, and you want to add 5 to an atomic something, how do you specify that 5? 5L, 5U, 5LL.
And if it's an atomic short, there isn't even a suffix for short, so you cast it. It's just, the original example I had for this was using atomic fetch add, but the compiler errors there were like 6 overloads that it could have been. It's like, I can't deduce this. I was like, I'm just going to create an example function instead of trying to use a real one, because the errors were just too annoying. Right.
I went and looked. There is no LaTeX package, or no Beamer package actually, which says take GCC compiler errors and make them fit on a slide.
Yeah, that's not going to happen.
Nor for Clang. I looked for one of those as well.
So yeah, the solution in a case like this is to stop the compiler from trying to use this t as a part of the deduction. So, this is what I've just explained to you. But yeah, the problem is that it's trying to use the same t in 2 different ways. So if we skip this one, because I've already covered it. So what you need to do is to create a non-deduced context. So this t is still in a deduced context, and it will still be deduced from the call. What we've done here is this t is now on the left of a double colon, which is a non-deduced context. There are a few things that the standard says are non-deduced contexts. This is sort of the easiest one to create and probably the most common one. Sometimes a non-deduced context happens when you don't mean it to, and you're like, why won't it deduce this? Here we're intentionally saying, I want you to take this t, do nothing with it, and then substitute it back into the template.
Don't we love C++?
Exactly. But you know what the cool thing about this is, Jonathan? Is now John can make a wristband for East non-deduced.
Yeah. So yeah, this literally says... This says, don't do anything with this. I just want you to stop trying to deduce the type from here. So now it will deduce only from this. We get long. Substitute long into here. Use our identity thing. Get long back again. And in the call where we passed an int, that int 5 will happily convert to long now that it's stopped trying to deduce it as an int. It's got long. So yeah, create a non-deduced context intentionally to remove certain arguments from participating in argument deduction. So this can be another place where you'd use this. String view actually requires this, doesn't it? And something very like this in its the plus operators for string views. There are a number of places where you need to say, and make sure you don't try and deduce this as a string view itself, because there are other functions to do that. But again, rather than creating a custom sort of identity thing, because identity is not in the standard, so we'd have to have underscore identity. But there's actually a nice trick. Instead of creating something that does nothing, the common type trait, which takes some number of types and says what would they convert to if you put them in a ternary operator, is actually the definition of common type. It's basically saying what would promotion and integer conversion and that sort of thing do to these types. So if you've got a char star and a void star, the common type is void star. If you've got
int and long.
an int and a long, the common type is long. If you've got a float and a double, the common type is double. The common type trait also allows you to pass in one type. And the common type of one type is itself. It's the identity transformation. So this saves us creating yet another underscore thing that we just use in one or two places.
Can you please create a PR paper to fix this in the standard so people laugh at us less?
So not have common type of one thing.
So that you just don't have to do it. The compiler just works out, oh, by the way, the second argument, forget introduce context, just make it compile. No, you can't do that.
Can't do that.
Write the paper.
Add it to min and max, please.
Yeah. But which one do you not want to deduce? Yeah.
One on the right.
Yeah, west min max.
All right, we got a question. We have a couple hands. We have a hand down here in front, and then over there.
Just to note that we will get identity in the standard, so in the group called type identity. And you just moved that forward last time.
Yep.
Type identity. Oh man, because those extra 5 characters are important.
Because people they use the value identity, which is what the range is using.
Maybe there's a reason for this and I can't see it. Why can't you just do template type name T, type name U, and have the 2 different arguments deduced as 2 different templates?
For this one, you definitely can, yeah. It wouldn't demonstrate the use of a non-deduced context if I did that.
So I'm just saying there are other cases in which you
Right.
Sure, yeah. So I think for the for the standard atomic ones, which was originally the example that I tried to use in these slides, the idea was that you didn't want to allow, or the standard didn't want to allow adding anything to an atomic int. It was sort of like, no, you shouldn't be having mixed arithmetic. If you've got an atomic int, the thing you're adding to it should be an int as well.
Or convertible.
Because if you try and even though adding 2 ints can still overflow, saying like, oh yeah, add an unsigned long to your atomic int is sort of asking for overflow. Not that adding an int to an int can't still overflow. And atomics don't overflow. I think they have, they're defined to have 2. Yeah.
They are.
So for that case, for the atomic one, you did want to encourage adding the same type to the same type. But then people realized, we've only just fixed this for C++ 17, the atomic things now create a non-deduced context for the second thing. Make sure it's the same type, but just don't let it participate in deduction. Yeah, for this one, you could certainly just say, you know what, just take whatever's on, just take anything. If you were writing a library where you wanted to be careful and constrain your templates and that sort of thing, and you had a U, you might want to constrain it so that, I'm going to pop back to the slide with the actual body of the function. Yeah, you might want to add a constraint that this operation would be valid on the U so that it wouldn't participate in overload resolution unless it would, otherwise you get an error inside this template. So you could add it as a second thing, but then if you're writing defensively or writing a very generic library, you'd have to do extra work to say, I'll accept anything, but not anything, only things that can. If you just accept one type, you don't have to worry about that. You know that t can be multiplied by t if it's an arithmetic type. But yeah, in practice, you may just say, take anything on there. Right.
And I would like to point out here as well that common type is a genuinely useful all over the place, and it is a customization point. If you have your own types and if you want them to be convertible to other types, you can customize common type. You can specialize common type for your types and say, I have this type and it's convertible to, say, long, or it's convertible to a string or something like that.
But you can only specialize it for the two-argument case.
Two-argument case.
You can't break this by saying the common type of int is long, or the common type of void star is char star. Like, no, not that.
Right. It's spelled out actually pretty carefully. Walter spent a long time spelling that out over and over again because we kept finding problems.
Yeah, we said, go and write it out 100 times.
But yeah, you can specialize. Common type can take an arbitrary number of types. You can specialize exactly the two-argument case where one of the arguments, at least one of the arguments, is your type.
And if you call it with 10 types, it'll sort of use the specialization for 2 at a time to get the common type of all of them. So when you specialize the two type case, that will get used for any number of them.
Okay, question down here.
When specializing, does the order matter? For the two-case argument?
Shouldn't do.
Shouldn't. I mean, you can write things that way, and you'll get surprising results, which will almost certainly not be what you want.
Can I say the common type of int and foo is long, but the common type of foo and int is char?
No, I'm pretty sure.
You should feel bad.
You will feel bad, yes. Actually, I think that in the specification it says that common type of AB and common type of BA need to be the same thing.
Yeah, so if you fail to meet that requirement, you have undefined behavior, which will probably show up in weird way. It's very unlikely to erase your hard drive in this case, but you don't know. If you provide a common type like that and we use common type in our library or someone else uses it in their library, you don't know which way around they're going to put them. So you may get surprising answers if you don't give the same. But I'm sure there's some clever way someone will come up with abusing that to do something that we all go, no. That's really smart.
Okay, next one.
So a generic wrapper like optional, this doesn't apply to any because any, as we saw, type arrays is the thing. But if you've got something like optional or tuple or pair that wraps something else, it's sort of generic object container.
Reference wrapper.
If you're just writing it yourself, you may not bother if you've sort of got optional of my class 1 and my class 2. You can probably get away with a quite simple definition of optional. When you're writing the version for the standard, it's got to cover every case. It's got to give the right answer for things like, is default constructible? Pop onto the next slide. If you're wrapping a T that is copy constructible, you want your optional to be copy constructible. And if you're wrapping a thing which is not copy constructible, you want your optional to
not be.
It will not be copy constructible anyway, but you want it to give the right answer when you query it with the traits.
Right.
Because then other things that say, can I copy this, can I put it into containers, they will get the right answer. Again, avoiding horrible template explosions deep down inside functions. So yeah, spin A again, of course, that's how we do everything. But you can't, because if the things we're trying to adapt are the special member functions, the copy constructor, the move constructor, that sort of thing, we can't just say, okay, so we will make the copy constructor a template. Instead of taking optional, we'll take something else, but then we'll constrain it so that only it happens when it is the same. So before we had the decay to say, don't use this constructor when it's my type. Here we'd be like, okay, yeah. This template should only happen when it's going to be a copy constructor and when the thing itself is copyable. So, yes, now we only have a copy constructor when the thing we want to copy is, or sorry, that should be T, sorry.
Yeah.
When the thing we want
Yeah,
to
T.
wrap is copy constructible. It won't work because this isn't a copy constructor. This is a
Converting
template. This is a converting constructor from U, even though we've constrained it to only do it when U is the same type. The compiler is going to say, no, I mean, thanks, that's great, well done for writing that. I'm still going to give you a copy constructor. Because that's what I do, I'm the compiler. So this doesn't actually work. You can't spin away a copy constructor because a spin can only work on a template. Concepts might allow this to be done a lot more easily, but we're not in that world yet in these slides. So yeah, you can't spin A here. So what can you do? Instead of getting the compiler to screw you over by providing the copy constructor, you get the compiler to help you and say, okay, fine, I'm just going to define it as defaulted. You figure it out, compiler.
Right.
You make this not happen if it shouldn't happen. Of course, it's not quite that easy because you've now got to, all you've done now is move the problem to, okay, how do I tell the compiler what it should do?
Right. By the way, that's kind of a general design guideline. If you find that the compiler is screwing you over and you're fighting it to keep it from screwing you over, maybe you should try a different approach and get it to help you.
Yeah.
Get it to do what you want.
Maybe trick it into doing what you want.
Yeah, that's which is what we're about to do.
Abuse it into doing what you want.
Abuse, baffle, trick, cajole. Choose your adjective.
So yeah, how do we, I've said that, okay, just define this as defaulted, but what I'm trying to trick it into doing is deleting it when I don't want it. So,
Equals delete.
yeah, and just assume no one will put copyable types into my optionals.
Well, no, equals delete plus the template, plus the converting templated one.
It will still generate a copy constructor.
If you say equals delete on the compiler generated one, and then have the template as well.
That
The type trait will
might work.
The type trait will lie.
Deleting one will be selected by overload resolution. Yes, the stronger match.
Yeah, so then when you try to copy it, the deleted one would get chosen and you'd find it's not copyable, yeah.
Use volatile.
I believe that using volatile file.
Use your template to convert to the constructor.
Yeah. If you use volatile, you've fallen into the trap of trying to not get the compiler to screw you over.
And you're using volatile and you should feel bad.
That too.
Yes, that will work because that will still be a copy constructor, but it's one that will almost never participate because, yeah. But this is what we really do because we don't like volatile in the library. So you move the problem to a base class, and now the compiler will say equals default. Okay, well that's going to depend on my members and my base classes and that sort of thing. So we have a base class which is parameterized by whether we want it to be copyable or not. And then in that base class, we have the default one. It can just be empty. Yeah, that's copyable. However, if the is copy constructible v was false, then we define this as deleted. And then when optional inherits from it, if t is not copy constructible, we get this. And then that means that the default here will go, oh, OK, my default is to delete it because my base class is not copyable. So we have persuaded the compiler here to give us the right answer for the copy constructor without having to spin it. We've just said, fine, okay, decide whether this is going to be provided or not based on this type trait. As always, it's not quite this simple.
Well, we've added a base class. Fortunately, it's empty, so it will take up no space, and none of its methods are actually non-empty, so there's no code generated as well.
What this doesn't show is how to solve the problem of the copy constructor doing anything useful. That has to happen in some other way, but what does happen with this is that it's deleted when you want it to be deleted. And that's all we're focusing on for this problem. But it's not quite that simple, because if you just said equals delete here, of course the compiler would say, deleted copy constructor. You're going to get no move constructor, no move assignment. So then your type's not movable either, and you may be putting something into an optional that is movable, not copyable. And so you need to explicitly list the other things. The rule of 5 say, okay, if we're mentioning one, we need to mention all the others and say, I still want these, even though I've said I don't want that. Just don't forget that anytime you mention one, you might end up affecting the others. And then on the, so we actually use some trick like this to get all the special members. Depending the properties of T, you end up with all the same properties being reflected in your optional. It's a lot of work, but you end up with a type which perfectly models the same properties as the thing you're wrapping. Yeah, just
Simply, no problem.
do it all.
It's not really that hard once you've written it 4 or 5 times.
In tuple and pair and
Yes, exactly. Once you do that, it's like, oh yeah, you just know, I got to do this, right? And you go find a piece of code, copy it, change the names, you're good. Or same technique, or maybe you automate this so you can just call it by name somewhere, but still.
Is copy pastable?
Is copy pastable.
Is there any code that isn't?
Well, you have all these base classes, maybe copyable, maybe movable, and you just inherit from all of them.
Yeah. Or in practice for optional, I think we have one thing that you inherit from, and it takes 5 balls rather than one type per property. We have one thing, and it's partial specializations for, well, if this is true and this is false, and then you get these members, and if it's no less work, but that's just how we do it. There was a question there?
Yeah, I would first, if you do actually derive from several empty base classes, and all compilers already support those, because I remember maybe a few years in the past, not all compilers would support multiple empty base classes to optimize in a way. So you had, like, for example, in boost operators, you had like things like base class chaining, where you just pass the other types to one of the base classes, and those which then pass again to the base class.
The Itanium ABI that GCC and Clang use certainly on non-Windows platforms, I think requires empty base. The EBO is required by the ABI, so the compiler has to, no matter how many you have, I think. It may not be true on Windows, but don't use Windows.
I think Alistair was first.
What that caught me out with not optimizing empty base is when you've got multiple inheritance that results in multiple copies of the same empty base.
Yes.
And each empty base needs to have a separate address.
Yes,
So
then it can't use it,
you
yeah.
can't get
Right.
that problem.
But yeah, because these are all distinct types, they can all exist at the same address, yeah. But yeah, it's possible that at some point you would have had a problem, and in my implementation, we don't actually do that, so I haven't experienced whether it causes a problem in practice.
Right.
So we made explicit take a Boolean predicated planning. Do we do the same with delete?
I don't think anyone suggested that. I don't think anyone suggested that in the form of a paper to the committee. Putting your hand up does not count.
I'm not saying
Yeah. It would probably come under, there have been a few things where people have proposed it and said, this would really help my implementation. And the committee have gone, you're a standard library writer, we're not in the business of making your life easier. Which is actually a fair point, in that if it's not going to help millions of C++ programs, it's going to help me and him and a couple of other guys. It's not the right trade-off to put something in the standard. We're like, but I really want it.
I know, but I really want it. Alistair.
You all gave a hint earlier. I think requires clauses will solve the need for having a bool on delete.
That's true, yeah.
At least for these common cases here.
Yeah, because you can, with concepts, you can put a requires on non-template member functions.
Which will help us a lot.
we had a discussion in evolution. I don't think that's enough.
That's right. I think someone said that bit had been dropped. Yeah.
Just to make your life harder.
Yeah.
Don't see you fix that.
Right. He's got the Inigo Montoya shirt. I just have the Man in Black quote. Life is pain, princess. Anybody who tells you anything else is just selling something. Standard library implementers are a bitter bunch. All right.
So, as you just mentioned, so you've already spoilt the final slide for this section. But yeah, another of the properties that you may want to sort of reflect in your generic wrappers is whether something's explicit or not. With the previous thing, the type traits where you say, is this copy constructible? You don't want them to give the wrong answer if you have optional of non-copyable thing. Here, it's not so much about giving the wrong answer, it's about doing the wrong thing, compiling when something would be unsafe. If you've got a sync that takes a unique pointer and you try and pass a raw pointer to it, it won't compile because the constructor for unique pointer is explicit. That's intentional to stop, to make you say like, no, this is a dynamically allocated pointer. Please do pass this into a unique pointer. You don't want it to just sort of grab any old pointer and then try and delete it later. Assuming we haven't fixed pair the way that we actually have done, but so in C++ 11, as it was first published, I think this would have compiled because pair has a constructor that takes two things and then it passed them to its members, its first and second, and the way those members were constructed could use explicit constructors because it would say first parens x, second parens y, and that isn't an implicit conversion. So you could have written that and say originally someone had pair of pointers, they changed its pair of unique pointer, and suddenly your thing is now grabbing
Right. Trying to delete something
the
on
address
the
of the
stack.
thing on the stack and then trying to delete it, yeah. So you want things like pair, optional, whatever, you want them to reflect the explicitness of the thing they're wrapping as well. You could just put explicit on everything. And then you're like, now you can't do anything unsafe, but then you also can't do safe things that are actually very convenient. So the way the standard, we did fix it for pair and duper and a number of other things. It defines it with capitals explicit in italics, which we can use because we're in the standard, but you can't use it in your code. So then it says like, when we say explicit, what we mean is that this may or may not be explicit depending on certain conditions.
Yeah, it's very much a hand-wavy trick.
Yeah, that when you see something in uppercase italics in the standard, it's sort of like, pseudocode here.
Yes.
So it says, like, yeah, this constructor is maybe explicit. The way you actually implement that is by having two constructors, one which is and one which isn't. And then you use our friend Svinay again to say, okay, so the explicit one will only get used when we want it to be, and the one that allows implicit conversions will only get used when we want it to be. Simple matter of programming to do the rest.
It kind of makes a hash of DRY, but hey. Don't repeat yourself. Oh, wait, I'm repeating.
Repeat everything.
Repeat everything.
Repeat all the things. So the actual conditions that you need, and this is only for pair, for tuple it gets, I couldn't even put one of these on the screen, I think. The conditions that you want are, obviously, you want to disable this constructor if it's not constructible. You don't want to accept U1 that can't convert. Oh, that's meant to be T1 and T2. I've done the same in both of these. No, it's not, sorry, no, T1 and T2 are the class, and this is, yeah, it is right, phew. So yeah, you don't want this constructor to happen if you can't construct the pair members from these types at all. And for this one, you don't want it to happen if implicit conversions would work. And so is constructible allows implicit conversions. Is convertible
Does not.
There's a U1, T1.
U-N-T.
That's where I got this. Yeah, I knew there was a typo somewhere. Yeah, it's right here. So you want, this one says use this constructor if it's constructible and implicit conversions are fine. And then in this case, you have to sort of carefully negate the conditions here and say, only use this if neither of these is true, because otherwise we get there. It ends up with a lot of code. Pair has become extremely difficult to implement because you do this for lots of different constructors, and tuple has even more, and it's a pain. But it works, and now we have, this is how you spell explicit in all caps italics. At least until the standard added a bool on the end of explicit, like no except true, false. You can now say explicit, true, false. So we can slightly simplify it by moving the implicit convertible bit into a Boolean constant for the explicit.
Well, if we could use that.
Yeah, we can't use that.
But you can.
Because our pair always has to compile, even in C++ 98 mode, so we can't do these things.
Right. Although there's no explicit in 98.
There's explicit, but there's no R value left.
Right.
Something, yeah.
Anyway, any questions about this? Yes, Peter.
Will there also be like no except an explicit operator?
No. But this is convertible. This is a type trait.
Okay.
Yeah.
Yeah, we don't need to add a language feature to detect that. There's a type trait that does it for you already.
Okay. Different case. I'm pretty sure that Scott Myers used an example very much like this in one of his, C++ book, one of his, modern C++ or, so on. You write something like this, or you see something like this. I'm sure nobody in this room would write something like this, okay? But you have something that takes two int pointers and it assumes ownership of the memory pointed to, and you want to pass them like this. New int, new int. The problem is what? The first new could succeed, the second could throw, and suddenly you have a leak. By the way, you have no idea which one is the first one and which one's the second one.
Second for some value of second.
Yes, right. For some value is first, for some value is second. And you say, okay, fine, I'm going to have to write some try blocks. Ooh, yeah, ooh. Right. We allocate one, and we wrap the second allocation in a try block, and if that fails, we delete the first one. Now, we don't need to wrap the first one in a try block, because if it fails, it throws, and that's fine. There's no leaks. But, ooh, this is annoying to write. It's easy to get wrong. If you have 3, it gets really ugly. Really, really ugly. Yes, Peter?
Do something might throw bad alloc, and then you forget to delete P2.
There's also that.
Do something's contract says that the things you pass it are cleaned up. That's what it says it in the name. It doesn't say do something and leak. Come on!
Anyway,
That's why I needed help for unique resource implementation.
Yeah.
but, I mean, occasionally you do see code like this in the wild, and it's like you try to clean it up, and like, no, this is not how you want to do it. So the good news is that unique pointer helps you a lot with this. If you and the other thing is that it might not just be memory. It might be some other resource, a file handle or something like that you have to allocate and then do something else which might fail, and you want to make sure you don't leak that. But unique pointer makes this really, really easy. Unique pointer, you do the first allocation, stash it in a unique pointer. You do the second allocation, stash it in a unique pointer. And then you pass those pointers, raw pointers, because that's what do something expects. You call release, and the unique pointers let go and say, it's not my problem anymore. I'm done with this. And do something is now responsible for all of this. Now, one of the things that, when I was writing this, I thought about, do you really need to put them both in unique pointers? Can you just put one of them in unique pointer and put like new whatever here?
All of them to the last one.
Yes.
No, you can't do that. That was the point I was making. Can you actually just do it all but the last one? You can't. And the reason you can't is because when you're building up the parameters for this, it might call da-da-da release before it calls unique, before it calls new, and if the new throws, then you leak. So you don't really have any control over the order things happen for the parameters. So you do have to put them all in unique pointers. You can't skip the last one.
Sorry, but if you had 1, 2, 3, 4, 5, and but then put the releases, except the last one alone. If you embed the new call in the do something call, yes, you're correct.
But yeah, this could be a raw pointer.
If you ensure the order by doing up 1, up 4, 3, up 4,
Right.
and the last up 4 for whatever reason is just a new, and then you put
Yeah.
the pointers in, you're okay.
Up
Yeah,
to
then,
here could be
then you're
raw
correct.
pointer.
But
Because you forced order, but if you put them in the order, in the
Right.
call itself, yes.
And someone could decide to refactor that and be like, oh, I'm just going to move that into the parameter list here, and then
Yes.
get back to the same problem again.
It's just all horrible.
I have the hypothetical intern that I use in examples. His name or her name varies, but it's like, we'll say Bob today. Bob is the intern you're going to hire next summer who's going to refactor this code to put the new call in the parameter list. Oops. Or the other example is, yeah, I know this is safe because it's only called from like 4 places in my code base, and I have preconditions in all those 4 places until Bob adds a 5th place. But in any case, this is an easy pattern to use. This is really easy. Just wrap it all in unique pointers, and then you're basically doing, you do all the things that can fail first, and that's here. At this point, all your failure stuff is done, and then after that, you do things that can't fail. The releases are not going to throw, and you've handed the responsibility for the pointers off to do something. Yes?
With the new C++ 17 evaluation order rules,
Yes.
can you use temporary unique pointers inside the call and then always call what it means?
No.
No?
Why?
Because, so yeah, if we imagine that this says unique pointer, open parens, new, or can it? Yeah, maybe it does say that the evaluation, no, I think, I can't remember. That's why I don't like the new evaluation rules, because even though I read them last week, it's still no clearer about what actually happens to my reading of it anyway. Peter, let's...
Yeah, Peter
first.
then Alistair. Yeah.
I thought about, why don't you inline that make unique? If the API of do something is broken, it takes ownership, so it should be unique pointer.
Absolutely, yeah.
And if it is unique pointer, then you can inline and make uniques.
Yes.
But it's
Yes, but it's not.
not. And because it's not, you have to have these separate variables.
Yeah, well, if you use make unique, there's no problem anyway, because the new is always inside a function, and it ends up, the news can't interleave before it's gone into so make unique solves it anyway. The case where we end up doing this kind of thing inside the standard library is, say something like vector, where you're allocating the new memory, and then you can copy everything over, and the do something, whatever it is, probably isn't going to take unique pointers, because we're deep inside the guts of vector at this point. So you may use it as a local variable, but you're not going to actually sort of re-implement vector with unique pointer in it. So
But you could.
if this was a public function, yes, it absolutely should be taking unique pointer to indicate the ownership.
Right.
Yeah,
And
turns
if-
out slides have bad examples.
Yeah, if you look at the blog post that is on that link, you'll see a more detailed example from the guts of libc++.
Alistair?
Yeah, the guaranteed evaluation order, 80% sure of this, but I believe we've mostly looked into it on the order of operations, but the next effect would be I construct the first shared pointer and release it, and then construct the second shared pointer, which comes from, and I've already released the first one, so it will not help you.
Yes.
Yes, because
It won't do
at this
anything.
comma, that has become an unowned raw pointer again. Yeah, thank you, yeah.
Other questions? Okay.
Which is, of course, not a problem if, as Peter says, you don't take raw pointers as ownership transfer.
Yeah. But this is slideware. And, it could be something that's not a pointer. It could be some other kind of resource.
Yeah.
Okay. Allocator construct. Allocators, contrary to their name, do more than allocate memory and deallocate memory. I'm sure there are people in this room who would be happy to go on for a long time, far longer than we have, about all the things you can do with allocators, but we won't. Anyway, besides allocate and deallocate, allocators can have methods called construct and destroy, and these are used to create objects from raw memory, to turn raw memory into objects, and to turn objects back into raw memory. If you don't provide these in your allocator, allocator traits will, in fact, provide a default implementation, which is exactly this, by the way. It will forward all the arguments to the constructor. It will do a placement new, and destroy will do a placement delete. But there's no requirement that your construct and destroy actually do those things. They can do almost anything.
As long as they construct and destroy.
As long as you actually end up with an object there. Some of the things you can do. You can log all your object creations and destructions. You can install an object in a global registry on construction and remove it on destruction. Note that you can't actually do that in the constructor and the destructor. You can do it in the constructor. The last thing you do is you register it. But you technically can't do it in the destructor because by the time you get to the destructor, the object's lifetime has ended. And so it's technically undefined behavior for something outside the destructor to call member functions on the object. So deregistering something from a global registry in the destructor is undefined behavior. And it will probably work until it doesn't.
But with the allocator, you can insert something here between this opening brace and the destructor call.
Right. While it's still an object, you can do things. And you can, here in construct, you can add parameters to the constructor. You can reorder them. You can ignore arguments that you're passed in construct and say, yeah, I don't care about that one. I'm going to just use these arguments. And yeah, in general, you don't do this, but you can if you have special circumstances. And this leads to, all right, I just said all these. You can decide what the default value for an object is. For objects created by this allocator, they can be other.
So you can, for example, have an allocator which intentionally doesn't default construct, but just leaves something uninitialized. Mm-hmm. If passed no arguments, you can make it, if you pop back to the last slide, you could add a construct for the case where that's just a pointer passed in, and not put parens or braces or here or anything, so that if it's a trivial type, you intentionally leave it uninitialized. Mm-hmm. So for people who get annoyed that when you resize a vector, everything gets set to 0. It may or may not work, because what the vector may do is, actually with vector it will work. It doesn't work with strings, because I think the stood string interface always copies a 0 into.
Right,
so rather than value initializing every member, it will instead stamp zeros on it, and so you can't do that.
Because it can use memset.
It can do that as well, yeah.
Calls char traits to get the value of the default initialized thing.
Yeah.
And then mem sets it in place. Okay, so we talked about this. So here's a fun example. I have omitted the code for the allocator because it won't fit on the slide. But vector standard allocator, we're going to initialize it with 5. Says we want 5 elements in the allocator. Vector with my allocator, 5 elements. Print out v1, print out v2, prints different things. Why is that? Because my allocator construct says, if I'm passed no arguments, I have a default, I initialize the int to a default value of 3. This is perfectly legal and even occasionally, very occasionally useful. As Jonathan has given an example of where you say, I don't want to do anything. So yeah, allocators do more than allocate. Who knew? Yeah, I know you knew, John. John's sitting down here biting his tongue. Okay. Tag dispatch. So when you're implementing an algorithm, frequently you want to take different approaches depending on what kind of iterators you're handed, what kind of characteristics of the data. For those quick review, there's 5 different kinds of iterators. There's input iterators, forward iterators, bidirectional iterators, random access iterators, and output iterators, which I'm not going to talk about because they don't really fit. But anyway, and you might want to do different things. For example, the algorithm find end takes 2 pairs of iterators and finds the last instance of the pattern in the corpus. Okay, the 2 iterators are the pattern to search for and the corpus to search. Okay, the most general implementation of that is you start at the beginning, you search for the pattern, then you search again, and then you search again, and you keep searching until it fails, and then you remember what the last successful search was. Okay, that's going to work all the time. But it's not as efficient as it could be. If you get handed bidirectional iterators, both the pattern and the corpus are bidirectional iterators, you just say you reverse them and start at the end and searching back for the pattern, and you find it the first time and you're done. Much faster, much more efficient, but only if you can run the iterators backwards. And if you have random access iterators, there are a bunch of checks you can do beforehand to speed it up even farther. You can eliminate a bunch of cases where you know it's not going to find. Like if the pattern is bigger than the corpus, it's not going to care anywhere. If the pattern is empty, it's like, oh, right there at the end. Or if the corpus is empty, it's like, nope, sorry, I'm done. And the other thing is if you know the sizes, which is what you get with random access iterators, then you can limit the search. You can know that the pattern can't start. If you have a pattern of 10, you're not going to find the pattern starting at 8 elements from the end. You can limit your search further. Anyway, but how do you do this? Because when you're writing the generic code, it's like, how do you do this? Well, iterator traits is your friend here. Iterator traits, you hand it an iterator type, and it gives you back a bunch of information about the iterator as a set of nested type defs. One of them is called iterator category. Iterator category is one of 5 things: input iterator tag, forward iterator tag, bidirectional iterator tag, random access iterator tag, and output iterator tag. And these are, interesting enough, related by inheritance. So what you can do is you can say, I'm going to call an internal version. Usually it's not called algo. It's usually got an internal name that's slightly different, but in this case, the compiler will help us with this. Anyway, this is a very, very simple algorithm. It's if you give it a first and a last of a sequence. If you give it random access iterators, it returns the first one. If you give it something else, it returns the last one. It doesn't actually do anything. But the point is that you say, I'm going to find out what the iterator category is. I'm going to create one of these, which is cheap because it's an empty struct, and I'm going to pass it. And the compiler is going to choose one of these 2 based on the iterator category. If I get random access iterator, it's going to take the one at the top of the screen. If I get anything else, input, forward, bidirectional, it's going to choose the second one because input, forward, bidirectional are all base classes of, forward and bidirectional are base classes of input, and they can be reverted to it. Is it that way, or I got it backwards?
Input's the base class.
Input is the base class,
So it will slice to that base.
It'll slice to that base, and slicing an empty class to another empty class is pretty simple. And it will select that. And this is used a lot in the standard library, in the algorithms. Like I said, find end, libc++ has 3 different implementations of find end, because you guys care about performance. You don't want us to do extra work. A lot of what we do is making sure that it's fast as possible so that you will use the stuff in the standard library and not have to go off and write your own.
And the advantage of, or one of the reasons for doing this is that the version that takes random access can use the random access operations. You couldn't just have one big function that does it all in one function because you can't use the random access iterator operations in the function body if you don't have random access iterators.
Peter?
Until C++17 will come to.
I have two questions. Why round parentheses for constructing the object instead of curlies?
Because we're old-fashioned.
Second question is, why not context for if?
You've been reading ahead. Stop that.
So in fact, I don't know if Marshall does this, because this is really tedious to write out and doesn't fit on a line, we actually have one of the tricks that only library, we have a function called iter category, or underscore iter category. And instead of having to put this annoying type name and colon, colon, whatever, we just pass one of the iterators to this function and it returns the iterator category. And then it would even fit on the slide, but it definitely fits in our. So that if you are doing tag dispatching on iterators a lot, I suggest just add a function that gives you the category when you pass it either of those iterators. Save yourself typing that rubbish out all the time.
Anyway, so yes, in C++ 17 and beyond, when you have context for if, you don't have to do tag dispatch hardly at all. You can just do this, and you can say, if context for is same iterator category random access tag, do random access stuff, else do non-random access stuff. And
this block here can use the operations on the random access iterator that aren't supported otherwise. Because one of the beauties of if context for is that the content here will not be instantiated unless the if is true. So you no longer have this thing of having to split it into multiple functions because you can't use some of the operations in the same place. This is the thing I mentioned in the panel yesterday that when I started using it. I'm just getting rid of, it's not just that you can write it all in one function, it's that these three functions end up with a lot of boilerplate. You've got to declare them all, and sometimes you've got to give them different names. And so avoiding having three implementations of find end or whatever it is, it's pretty nice to be able to keep it all in one place and not have two versions at least of every function. Peter?
Also, you don't fall in the trap if you have multiple overloads to have them in the wrong sequence and use them before you have defined all. Remember Marshall? we have had that problem in the past, yes. Lisa.
Don't you, in general, want to use is convertible rather than is same here?
In general,
No.
yes. For random access, it shouldn't matter because that's the most derived. There isn't anything deriving from it. But yes, yes, like contiguous or yes,
or something like that.
And in that case, you wouldn't want to use the iter category helper that I said because otherwise you'd end up having to decal type it. Here you do want the type. So in the previous one, we actually wanted an object of that type. Create the tag to pass to the other function. For the if context where you don't want an object, you are just literally asking about the type.
Yes.
Do you use is convertible instead of is same?
That was her question, and
I'd actually use is base of, not is convertible, but yeah. It should probably be slightly different to this, yeah.
Alistair.
Can I C++ 20 code by omitting the type name?
Yeah. Yes, one of the cool features that's recently being approved is no longer needing to put the type name somewhere where it's obviously a type. Compilers having all finally sort of got strict enough to be like, you didn't put your type name there. I know I used to accept this code, but now I'm required to not accept it. The standards have now been changed so that the compilers can again go like, okay, I knew all along it was a type. You don't have to put type name anymore.
Yeah.
Just as everyone's gone and put them all in everywhere they were needed. Now you didn't need to do that.
Yes, down here in front.
As a matter of personal taste, do you find this version with context for if more beautiful than tag dispatch? Because yeah, you do have fewer overloads, but you have all this code nested inside one big function, and you could say it breaks separations of concerns in terms of different approaches to implementing the same algorithm?
Let me answer and then Roger's answer. So with this approach for short things, it works really well. For longer things, you can just write call a function, else call another function. But it seriously reduces boilerplate. It reduces of this one, 1, 2, 3, 4 lines, it gets rid of 3, 1, 2, 3, 4 lines, gets rid of 3, and gets rid of this. It replaces them all with basically a single if-else. And so for that, yes, it works pretty well. Roger?
You can still split things up into separate functions if you want to split things up into separate, that's just good programming. But you don't need to use the tags anymore to dispatch. You can just have you could have algo underscore random and algo underscore input and call them, where without the context for if, you can't even call those two different ones because it will instantiate both, and one can't be instantiated with random access. That one can't be instantiated with input iterators. So you can still split it up, but it's still easier just to use than tag. I mean, I love tag dispatching, but it's still easier not to have to do it.
And if the implementations differ only in like one line, you now put the context for if around that one line, and you have avoided repeating yourself in your multiple implementations.
Yeah.
Also, it's a template, it's not supposed to be.
Alistair.
Reading ahead, can you contrast this with using concept and concept-based overloading?
No. We didn't. Our library hasn't been conceptified yet, so that's not a trick that's as an implementer am using yet.
So we can't trade off to know when one is better than the other yet. We don't have that experience.
I can't give you that answer. Yeah. Hopefully someone else can and can tell me.
Okay, we have questions. Oh, I forgot to mention that the usual caveats apply here. When somebody says, I could tell you that, but then I'd have to kill you. Well, we forgot to say that at the beginning of the session, so we're going to have to kill you all.
Yeah. Close the doors, no one leaves.
He's first.
You do.
Oh, somebody's sneaking out. Get him! Get him!
Sorry, just the green card in there, don't worry.
Okay. Yeah, and that's the other thing is, anybody puts a yellow or red card in, man, we're going after them.
Yeah.
Other questions?
I do have a question. We just saw the if context expert, and on the other hand, you were telling that all your code has to compile C++ 89. So how is that being done in practice?
My compiler allows this at least in 11. Yeah, in 11 because context was not a key. So GCC will in system headers. So I can use that. Except I can't because our library wants to work with Clang and GCC, and I think Clang only allows it in C++ 17. So
Right.
I kind of could use it, but then I'd break people using Clang with my library, and I want to support that.
And
Which is annoying.
new features.
Yes.
New features which are bracketed by, if def C++ 17 or later, we can use that just fine. But old features, not so much.
That's right. That's something we meant to mention earlier is that, in the implementation of variant, we can use all of these tricks. In the implementation of pair, it's, some of them you can, some you can't.
Right.
And sometimes because we're the standard library, we happen to know that our compiler allows this in. So like variadic templates, GCC will allow in 98. I think it will warn you and say, you can't do this, but I'll allow it. It just warns you and tells you that you can't do it, and it works fine. And again, it may be the same for if context, but it might go like, that doesn't work. It works.
It works.
And in system headers, so for me, it doesn't even warn. It just sort of like, fine.
There's
no point warning me that my own compiler does something that I know it does.
there's a lot of back and forth between a standard library and a compiler. They tend to be. It's not joined at the hip because we can work with other compilers, but there's definitely a lot of things that the compiler can do to make a standard library writer's life less miserable. Alistair.
Does the compile time benefit of having fewer templates discovered, instantiated in name lookup, ever justify conditions saying, well, even though I can have the one implementation that works all versions, I will still do the other implementation just for the compile time throughput? And yeah, if you take the condition, the features.
I haven't measured it, but yes, there can be advantages to it. And as I said, if you had excuse me, if you had algo underscore random and algo underscore input, you're no longer doing overload resolution with the tag dispatch. You know, you're just saying call that one. So yeah, you can. There are lots of ways to slice these things up and say I'm still going to separate it, even though we've got if context. But I haven't measured the differences with throughput.
That's what I was also wondering with all the concepts versus
Yeah.
if
Right.
context,
Yeah.
again, with just the future overload sets that you might still do.
Right.
Yeah.
Although my non-scientific, non-measured experiences, overload sets of size 3 are not really such a big deal. It's overload sets of 50 or 60 or 100 stream insertion operators that really, really bog down compile times.
I'm not sure how optimized the concept implementations are at the moment anyway, whether today's concept compilers are as efficient at, whether saying it's a good measurement today, because it may be that once we all start using requires clauses, the compiler, the concept implementations optimize that better. So you might get numbers today, but they may not still apply in 2 or 3 years.
You keep putting S's on the end of your nouns.
There's GCC 7 and GCC 8 and GCC...
And GCC trunk. Any other questions? All right. I guess we're done.
Nope.